the last section. You are so going to love this. There's so much math. There's so much notation. It's enough to make you puke. I can't wait. It's going to be fun. Okay, so first let's do a little review. We have the area of a circle is pi r squared. If I want the area of a sector of the circle, well, this is the fraction theta over 2 pi. So we have that fraction of the area. So the area of a sector is theta over 2 pi times pi r squared, which simplifies to theta r squared over 2. Now let's apply this to how to find the area of some generic region done with polar coordinates. So here's our generic region. It spans or goes from alpha to beta. My function is defined by r equals f of theta. Just like what we did back in regular calculus, or this is regular calculus, just like we did before in Calc 2, we're going to break this up into smaller pieces and make the pieces smaller and smaller and add up the area of each of the small pieces. Take the limit as n goes to infinity. That'll give us the area of the whole thing. So we've got polar coordinates, so instead of breaking this up into rectangles, we break this up into sectors, like that. So we're going to look at each of these sectors and find a generic name for the area of this thing, and then make them skinnier and skinnier, and then that'll give me the area of the region. So let's do some labeling here. I'm going to let theta star of I be that middle angle in here. So whatever's between the two of these things. We did this back in Calc 1 or Calc 2, when you did the area of the rectangle, you would choose the left point or the right point to figure out the height of the rectangle. Sometimes you found the middle point. Doesn't really matter. You can choose any point in the middle because you're going to get smaller and smaller anyway. So I'm just going to pick the middle one. So to find the area of this region, we're going to add up each of these sectors. So what is one sector? We have the 1/2 r squared theta. In this case, my theta is actually the delta theta, and that's what we're going to make. We're going to make smaller and smaller. So let's look at the formula. So here is my 1/2, my r squared, and there's my theta. Now we're taking the limit as n goes to infinity, which means this is an integral. So anything that has a star on it becomes the variable. The delta theta becomes d theta. Oh, I'm tongue-tied this morning. So there's my equation. Typically, we instead of writing f of theta, we'll go ahead and just write r squared, or r, f of theta. So let's look at an example. So let's say we have r equals cosine theta, and I want to find the area of these 3 petals. Notice that they're all the same area. I can just find the area of one of them and multiply by 3. Another thing is we need to know where alpha and beta are. What are our limits of integration? Well, 3 theta, or cosine is normally 0 at negative pi over 2 and pi over 2. But since 3 makes it 3 times faster, we're going to go from negative pi over 6 to pi over 6. So my integral, 3, because there's 3 petals, I go from negative pi over 6 to pi over 6. There's my 1/2, my r, and my theta. So to integrate, now we're just in normal integration. If we want to integrate cosine squared, we use a cosine formula to get rid of the square, double angle formula, if that's how you look at it, or the square formula. It depends on your perspective, which one you're looking at. So I'm going to plug that in. Now, I took the 1/2 out and the 1/2 from my formula to get a 4, because I don't like all those nasty fractions in there. So integrating this, we get theta plus sine of 6 theta over 6. We're taking it from negative pi over 6 to pi over 6, which, when you simplify it, is pi over 4. I'm not going to crunch all that out. You know how to do integrals. So now, what happens? Let's go to 3 space. When we want to integrate over a region, but my function is in the height. It's a function of x and y. We're looking at z. So same idea as what we did. Actually, we didn't do this. I kind of skimmed over this part, but I'm going to do it better now. We're going to break this up into smaller pieces, and we're going to integrate over each piece. So we have what they call polar rectangles, because they're not really rectangles, they're curvy. And we're going to focus in on one of these, because those are too many. I want to pick a point in the middle, just like we did with the theta star I. I want to figure out a generic point in the middle, an r I star and a theta I star or j star, because I need different subscripts. I'm just going to take the average of the two. So this will represent my theta j. This represents theta j minus 1. My I minus 1 Ri. So this is my generic box I'm going to integrate over. Imagine we're going to make these boxes smaller and smaller. So when I integrate, I will have so my Ri is the average of my i's. My Ri star is the average between Ri and Ri minus 1, and etc. The theta star is also an average. So let's look at the formula. I have to look at the change of area. Well, this area is represented by, let's find the area of the big one. Let's see if I can do a pen. So I find the area of the big sector. Oh, wow, I cannot draw. And then that's this one. And then we subtract off, that's the big one. And then we subtract off the little one, which is here. Okay, let's just get rid of that because that's just making a mess of things. So notice that I have a 1/2 at the beginning and a 1/2 at the beginning of both of these, so I can suck them out to the front. And I've got a delta theta j that I can suck out to the other side. Then I'm left with an r squared I minus 1. Difference of squares, I can factor it. So, point of all that, I can simplify it to this. Now the reason I want to look at it this way is notice that this right here, this was Ri star. This is delta R. So now we can simplify that a little bit further after I clean it up. Oops. To 1/2 Ri star delta Ri delta theta j. I should just not talk during this. I should just point and say that because I'm going to get more tongue-tied. So let's figure out. So these are our change in variables. My theta goes from alpha to beta. My r goes from a to b, and we've got to have the function in the middle. Now the function has to be in polar coordinates, so it's f of x, y, but my polar x is r cosine theta, my polar y is r sine theta. So let's rewrite all this in terms of messiness. This we really can't fix, but this I can rewrite using what I figured out on the previous page. So I have all this mess. Now to integrate this, I want to take the limit as m goes to infinity and n goes to infinity. Another way of saying that is that these deltas go to 0. So the integral of my function over the area is the limit as the deltas go to 0 of this summation of f of crap delta aij. Delta iij, remember, was Ri star delta Ri delta theta j. I should have kept with that. Don't talk, Megan. Now, we've got the limit. We've got these guys. When you take the limit, you can get the integral. You'll get the integral. The stars turn to variables, and the deltas turn to d's. So the integral over r would be, oh, wasn't that helpful? I wish I'd realized I'd done that before. So our integral becomes alpha to beta, a to b of my function. Don't forget that r there, dr d theta. So that's how we integrate a function over the region dr d theta. That's how we integrate f of x, y over the region R. Let's look at an example. Suppose I want to evaluate x plus 3y squared over the region R. R is bounded by the circles x squared plus y squared equal to 1 and x squared plus y squared equal to 4, and y is greater than or equal to 0. So checking out what that actually looks like, we have this half a washer. I went ahead and drew my little subsection there so you can kind of keep that in mind. So I'm integrating, well, theta is going from 0 to pi. R is going from, let's see, this has a radius of 1, this has a radius of 2, so R goes from 1 to 2. I need to plug x has to be r cosine theta, y is r sine theta, and then we multiply by r and get this mess. Now, before I integrate, I'm going to run the r through. And this is not going to fit on this page. I have, if I integrate with respect to r first, that's not too bad. I got r cubed over 3, 3r to the 4th over 4. That's no big deal. Ooh, fractions suck. Have to plug in the 2, subtract the 1, go to the next page. And we get that when you clean it up. Now, again, I have a sine squared. To integrate a square, you have to use a double angle formula for sine, which is 1/2 1 minus cosine of 2 theta. Integrating that and simplifying, you get 7 pi over 2. Straightforward integration once you get it set up. The setup is the hardest part. So I will probably have another set of slides with some practice problems, but no promises. Good luck with this. It's our last section. Only 2 more weeks. We can do it. We can do it. I miss you all.